My name is Vineet. I'm a PhD student at MIT. And today I'll be presenting our work on circuit-aware distributed optimal voltage control for distribution grids. And this is work with my advisor, Anu Anuswamy at MIT, and Luca Hartmann and Florian Dorfler at ETH Zurich. So the motivation for this work, So the motivation for this work is if you look at traditional distribution grids, so medium and low voltage networks, they are generally connected to the transmission grid. So they rely on centralized large power generation units like coal and natural gas. And all of these generators are synchronous generators, so essentially large rotating machines. And so they have a lot of inertia and natural time delay. And so they have slower dynamics than the grid circuit dynamics. But if you look at the distribution grids of the future, they'll be much more independently operated and relying less on the transmission grid, because we'll have a large number of smaller inverter-based resources directly in the distribution network, such as solar PV, wind, or batteries. And these are based on power electronics, which have a much faster dynamics than synchronous generators. And so they offer little to no inertia or delay. And so because we have fast power electronic dynamics, these are faster than these are still faster than the power grid circuits, but more comparable than the synchronous generator dynamics. And so prior works deal with these fast dynamics by artificially slowing them down using virtual inertia with batteries or some low pass filter based troop controllers. But the main disadvantage with these modeling approaches is that they require a very large, expensive energy storage units when you add a lot of inverter-based renewables. And the alternative is to allow these fast power electronics dynamics. But then because these become comparable to the circuit dynamics, we also need to model the fast circuit dynamics, which we do in this work. And so these are some of the challenges that we are considering for the future grid. So the first is that we have these dominant fast circuit dynamics, but they're not currently considered in the control design of inverters. And then we could also have scenarios if we have a large number of IBRs or distributed energy resources, we can have complex interactions between these that can cause oscillations and instabilities or inefficient power dispatch. So this is just a summary of the work that we'll be talking about today. We'll just be considering the problem of voltage control. So say we have a large increase in load at this node 17, we would have a undesirable drop in voltage at that node, and it also affects the voltage at other nodes in the network. And then the idea is to use a hierarchical voltage control to try and restore that voltage back to the level before the load step. And so this is done in 3 steps. The first is tertiary control, which is basically a market clearing or dispatch, and which we use using a market structure that was developed in prior work. And then the second is model predictive control for secondary control while accounting for the circuit dynamics model. And this helps reduce the voltage oscillations with a greater efficiency in the dispatch. And then the last method we develop is a distributed solver for a clustered distribution grid, which allows for more modular and scalable computation. And it requires only local changes when you have local updates to the network. And finally, we present a scalable simulation of multi-IBR power grids with the circuit dynamics. First, we'll just talk about the circuit dynamics. So if we consider this distribution grid, so this is a test case. And if we just consider, say, the line connecting nodes 5 and 6, we use the pi circuit line model, which is very commonly used for low voltage networks. And it's essentially just modeling the distribution power line as having some resistive and inductive elements with some capacitance to the ground. And then for simplicity, we model the load as being purely resistive with some admittance. And so using that, we can derive the passive circuit dynamics. So the dynamics of the power line, that is the RL element. And then we have the dynamics of the bus, which includes the effects of the capacitance and also the resistive load. And so if we combine both of these, we get the passive grid dynamics in a state space form, which we can then use in the in the control strategy. And then we also need to add in the effects of primary control. So primary control is the fastest timescale control that is directly done at the inverter level. So most inverters that we see today are grid following, which essentially means that they just absorb or inject power based on the grid voltage or frequency, but they can't really influence the grid voltage or frequency, so they can't operate independently. But we have considered grid forming inverters in this work because we believe that they'll be more common in the future because they can actually set the grid voltage and frequency by acting as a voltage source. And we also make some assumptions that the voltage and current control in the inverter are in steady state. And we also assume ideal behavior within the power range of interest that we consider. And so we just use the normal primary control, which is not the focus of this work. So we just use a conventional group control, which essentially deviates the reactive power reference to influence the voltage. And so if we add that primary control dynamics to the passive dynamics, we get the full grid dynamics that we can use to describe the primary control. And then we can use this for our secondary control strategy. And so for secondary control, the idea is that if you have a disturb for the simple 4-node network, if you have a large increase in load at, say, node 1, that causes the voltages at the other nodes to deviate. And as a result, the reactive power also changes. But then by changing the reactive power set point at different nodes, we can restore that voltage back to that the case without the disturbance. And so this is achieved by regulating the voltage by changing the reactive power reference. And the traditional implementation we use is an averaging proportional integral control, which essentially looks at the average voltage deviation in the network and then comes up with the update to the set point, and then it applies the same set point change to all the inverters in that network. So this is just an overview of the control hierarchy. So at the fastest time scale, we have a primary control, which is local to each inverter, which essentially controls the voltage by looking at by deviating the reactive power based on the deviations in the reactive power and the measured reactive power. And that feeds into the power grid with the load and other inputs. And then secondary control essentially looks at the measured voltages in the network and comes up with the set point changes that are needed to regulate the voltage. And then tertiary control is the market, which is at the slowest time scale. And it essentially sets the reactive and the active power set points. And we performed secondary control by solving the market clearing by solving a current injection based optimal power flow problem. I won't go into the details of that, but you can refer to this paper in the prior work to see that. And so a brief overview of model predictive control, which we use for secondary control. And this is a control approach where we use forecasts to optimize your actions over a certain number of time steps into the future. And then you apply the input only for the very next time period. And so that planning horizon is what we call the period over which we optimize into the future is what we call the prediction or the planning horizon. And the reason we want to use secondary control, we use MPC for secondary control, is that it allows for a very intuitive objective. So in this case, we can consider voltage tracking and loss reduction by controlling how much controlling the control input or actuation. And then we can also better plan ahead for bounds because we are looking ahead into the future. So we can avoid hitting generator limits. We have more degrees of freedom for cases with multiple IBRs. We can reduce losses by more local actuation. And we also need very little parameter tuning to achieve good performance. And we can achieve a fast, stable response with less oscillations. So this is the MPC optimization problem where we have a cost function with L2 penalty on the voltage and a L1 penalty on the reactive power, which essentially promotes sparsity. So we are not changing set points at too many generators. And then we have the discrete linearized grid dynamics. So this is the primary grid dynamics that I described earlier. We have initial conditions and bounds on voltage and generation. And so in a traditional centralized MPC, if you have a single processing unit that takes in the information from each of the devices, so each inverter at the nodes, and then performs the MPC for the entire network and sends back the set points to each inverter. But this is not ideal in many cases. So if we consider a scenario where we change the topology and add a feeder to the network, and we know that the distribution grid is actually changing very rapidly today as we have more resources being connected, we'd actually have to change the entire centralized MPC scheme. So an alternative approach is to use a distributed method where each node or inverter mostly uses local information to determine their optimal set points, but it also uses some information from the peers or the neighboring nodes. But we can minimize the amount of communication that's needed. And so the idea here is we can separate the grid into multiple clusters. So here we considered a case study where we divided the network into 5 zones, and we solve a distributed optimization problem that allows us to separate the computational burden. And it's also more resilient against local failures in a particular cluster. And it enhances privacy because you don't have to exchange sensitive information between clusters or with a central unit. And also local changes stay local. So if you change the topology, it involves minimal changes to the distributed scheme. And so I won't go into the details of the DMPC, but the idea here is to derive coupled cluster dynamics, define the distributed MPC optimization problem. So here we have 5 clusters, and we bring it into a standard separable form for the solver. And then we solved it using an algorithm from the literature, which is based on this this approach called ADMM. And so you can refer to this paper for more details on that. And so the dynamics look very similar to what I described earlier. So the dynamics within each cluster remain the same. So you have an internal cluster state and input, but the main difference is that now clusters have to exchange a subset of the variables with their neighboring nodes. So in this case, that variable would be the connection current. So the cluster A is connected to the next cluster at node 18. So it has to exchange that edge current. And then it also maintains the copies of certain variables. So in this case, it has to have a copy of the voltage at the node in the other cluster. And then it has some extra constraints to ensure that the true voltage of that cluster matches the copy maintained by cluster A. And so the optimization problem looks very similar, except we now have this cluster dynamics, and we have some extra constraints for the copied voltages. And I present some simulation results on a realistic feeder. So we took this IEEE test case and added 9 IBRs to the network. And we simulated the network as a microgrid, which means that there's no power from the transmission grid. And we introduced a large increase in load at node 17. And the first idea is that the PI control, as we know, can be unstable without tuning. So it requires a lot of changing of the controller gains and parameters to ensure stability. So in this case, we see instability, and it clearly violates like some of the voltage stability limits that are set for the network. And then even when we stabilize the PI control, we can see that it eventually does return back to the so this is the load step, the voltage drop at the node with the load due to the load step. And these are the voltages at all the other inverters or the generators. So we see that it takes some time for the voltages to settle back to the steady value, the nominal value, and also there are some oscillations. Whereas with MPC, we have almost no oscillations, and it's a very fast, stable response, and we don't really need to do any tuning to ensure stability. And this is just zooming in to consider only the generator nodes to show more clearly the oscillations with the PI control and the very smooth response that we get for most of the nodes with MPC. And similarly, we see that MPC can also help reduce deviations and oscillations in the power injections for both active and reactive power. And so we can see that here, the power injection changes are much smoother, and also we have almost no deviations in most of the nodes except for those 3 compared to the PI. Then we also wanted to compare the control inputs. So if we see the PI control, the way it works is that it averages the voltage deviations. And so we have the same change in set point at every generator, which is not really ideal. So we require very large set point deviations at all the generators. Whereas with MPC, we see that the voltage deviations at most of the nodes are smaller. So we only need to change, and we can change the set points individually at different generators, so it's more flexible. And so we can rely on IBRs that are closer to the load step. So if you see here, for example, because we have the load step at node 17, we see that the reactive power set point is changing most significantly at the generators at node 4 and 16, because these are closest to that load step. And so this is essentially a more efficient way of solving that voltage control problem. And it also helps reduce the power losses. So the MPC has around 11% lower network losses compared to the averaging proportional integral approach. The main conclusions here is that the MPC with circuit dynamics is better suited for grids with IBRs. We have a distributed algorithm that's more modular and scalable. And the future work, we want to test on larger grids with more IBRs, consider other load models, and extend to cases with limited measurements. Thank you.
Myself, one question about the pursuing that information. How is that? Was there some sensitivity way of valuing the network infrastructure and
So this one we actually just did it manually because there are already like zonal that have been defined, like 5 zones. But there are approaches that you can use, like a cut set algorithm or optimal ways to cluster the network. But we didn't implement that in this work. Yeah.
this well, was this many kind of Thank you.